Hi, everyone. Welcome. Our next speaker will be talking to us about statistical profiling and other form of the SEAS model. Please welcome Emin Martinian.
Thank you very much, and thanks for coming to my talk. So today I'm going to tell you about why you might want to do statistical profiling. I'll tell you about some of the various Python tools that are available, and I'll give you some details about the OxProfile statistical profiling package, which I've written. The slides and the source for all of this is on GitHub at the address below, so you don't have to take notes or anything. Okay, so we're going to learn how to use profilers, and hopefully you'll also learn how to write your own. One of the things I really love about Python is it gives you access to the internals of the system in such a way that you can do things like debuggers, profilers, code coverage that would be very difficult, at least for me, in a language like C. So let's start with what is profiling. According to the python.org website, a profile is a set of statistics that describes how often and for how long various parts of the program are executed. So profiling is basically useful to find out which parts of your program are slow. That way you can spend your efforts in optimizing things and writing really nice, tight code in the parts of the program that really matter. So for deterministic profiling, there's a number of profilers you can use. cprofile is one of the built-in profilers. It's very easy to use. You do import cprofile, and then you do cprofile.run, and you give it a string for the function you want it to run. It'll then run your code, and it'll give you back what's called a profile, which tells you how many function calls there were, how often each function was called, the total time, the per call, cumulative, and it'll rank them in order of the function that took the most time. So then you can look at that deterministic profile and see which parts of your program were slow or took longer than you thought and work on optimizing those. So again, that's deterministic profiling. So how does deterministic profiling work? Well, the sys module provides you a couple of really neat hooks. One of these is setProfile. So if you call sys.setProfile, you can give it your profiling function, and then the interpreter will execute your profiling function on each function call. And if you want even lower granularity, you can call setTrace, which is like setProfile, where you give it a tracing function, and then the interpreter will call your tracing function on every single line of your program. And you can use that to figure out what code coverage is, or what parts are slow, or whatever else you want to do. Okay, so once we call these things, we get a hook to inspect the stack frame. So you might say, well, what is a stack frame? So the way the Python interpreter works is you have some function foo, let's say, which calls a function bar, which calls a function baz, which calls a function boo, and so on. And the interpreter needs to keep track of the state of each function, the local variables, and what's going on. So it creates an object called the stack frame, which we show here. And the stack frame has a number of interesting things. One of them is fback, which points to the caller's stack frame, so you know where your function got called from. There's also fglobals, which tells you which globals you can see. There's a lot of other useful things in there. The one we're going to focus on here is fcode. Fcode is a code object, which is shown in that elliptical feature there. And the code object has a lot of information about exactly what code is running in that frame. It's got the co-file name, which tells you the file name where it was created, co-first line number, which is the number of the first line of the source, a bunch of other interesting things, and co-name. And co-name is the one that's most interesting for us because it gives us the name of the function that is executing that stack frame. So for a profiler, you look in the stack frame, you look at the code object, and you look at the name, and now you know what function is executing, and you can keep track of that. Okay, so let me give you a diagram of how how deterministic profiling works. So you have your program, it's in its main thread. Let's say there's some loop that's going to execute function 1, then function 2, then function 3. So what happens is the interpreter enters function 1, and then immediately calls that profiling function you've given to sys.setProfile. And then your function will record the name of the function that's executing by looking at the stack frame, what time execution starts, and then it'll pass control back to the main interpreter, which will execute your function 1. Then when function 1 is done, the system will call your profiling function again. You record the function name, the end time, and then you pass control back to the interpreter. And then the interpreter moves on to function 2, and similar things happen, and moves on to function 3, and again, your profiling function gets called to record the name, the start time, or whatever other things you want to record. So the key idea here is that for each function call, your profiling function gets called. Or if you're using setTrace, for each line, your trace function gets called. So that's great. It gives you really detailed information about what's going on. But the downside is it's slow. These hooks have to run for each line or each call. So deterministic profiling is great, but one of the drawbacks is it's slow. Okay, so what's another drawback? Another drawback is C number 1. It's slow, and I mean it's really slow. And so this is important because it makes it difficult to use profiling in production, deterministic profiling in production. So deterministic profiling is very useful when you're in the development stage. You want to run some tests, you want to run some use cases, you want to see where the bottlenecks are, you optimize it, you write great code, fantastic. And then you deploy that in your production web server or your consumer application, what have you, and the users do all kinds of crazy things which you didn't expect, and they complain that your awesome program is slow. And they often do that because regular users may not be programmers, so they're going to use it differently than you. And so that's a problem with deterministic profiling. It's harder to get the production experience. Another, you could say drawback or just kind of a difference in focus, is that deterministic profiling usually is not thread aware. So this little blurb is from the documentation for set trace. It says, it must be registered using set trace for each thread being debugged. And there's similar documentation for set profile. So that is, out of the box, deterministic profiling doesn't handle threads really well. And it's not so much a drawback, it's just kind of the way threading works, which is, imagine you're in some function foo, and your profiling function gets called and says, okay, we're in function foo starting at 2 p.m. And then there's a thread switch, and the interpreter starts running function bar, and function bar takes a long time, and then the interpreter switches back, and now it's 2:05, and function foo finishes, and your deterministic profiler says, well, function 2 just took 5 minutes to run, even though function foo maybe is really fast. And so that makes profiling threaded code a little bit complicated. You can do it with deterministic profiling, but it is a little bit complicated. Okay, so what we're going to talk about for the rest of this talk is a statistical profiler. Now, the way a statistical profiler works is you have your main thread, you still have your function 1, function 2, function 3, just like before, but the statistical profiler is going to record a sample of which function is running. And it's only going to run occasionally to keep their overhead low so that it doesn't slow down your production code and you can actually run it in production. So here's a diagram of what it looks like. So again, you have your main thread running, and then you have a sampler thread, which is either another thread in your Python program or maybe a completely separate program. What the sampler thread does most of the time is time.sleep, so it does nothing. Every once in a while, it wakes up from the time.sleep, and it peeks in to see what the main thread is doing. Which function is it running? And then it records the name of that function, and then it goes back to sleep again. So it's basically kind of waking up periodically and seeing what you're doing, and then going back to sleep. Okay, so how do we implement this sampler? There's a couple different ways, and there's packages for each approach. So one thing you could do is use the POSIX timer. So the POSIX timer is a low-level timer. You can set it to wake up and interrupt your process. And when you get that interrupt, you can check the call stack, see what the call stack is doing, what function is executing, and keep track of things like that. A couple of programs that use this are StatProf and Plop. So those are great programs. They're not available on Windows because this is a POSIX call. Another way you can implement a statistical profiler is something called ptrace. Now, ptrace is a really neat system call in POSIX. It lets you look at what some other thread is doing and control it or inspect it or whatever you want. And ptrace can actually be called completely outside of your own program. So if you're familiar with something like GDB, GDB works along these lines, which is you have your program that's running perfectly fine. It doesn't know anything's different. And then some other program like GDB or a profiler will use ptrace to reach into your running program and pause it or see what's going on in the stack or otherwise inspect it. So that's how PyFlame works, which is a very popular and nice statistical profiler. It's not available on Windows because this is a POSIX call. Okay, so you might say, so I've mentioned two approaches, both of which are POSIX, and so you might say, do we really care about non-POSIX? I mean, a lot of us use Linux, a lot of servers run on Linux, why do we care? So one answer is, it's nice to have a portable implementation. That is, all other things being equal, it's nice to have something that's pure Python, that's easier to move around to different systems, in case, for example, you want to use Windows. Another reason is using only Python features makes it a little bit easier to understand for those of us who are Python experts, but maybe a little rusty in OS internals like setTimer or ptrace. And in particular, if the whole goal of using a statistical profiler is so you have a low overhead profiler that you can run in production, it's nice to have an implementation which is easy to understand. It's pure Python, so you can look at what's going on. And then we can get confidence that this statistical profiler you're using in production is not going to mess up your code. Or if, heaven forbid, it does mess up your code, you can at least figure out why and go yell at the maintainer. The third reason is there actually is software, believe it or not, that does run on Windows. One good example is games. There's lots of other consumer software. To take games as an example, if you want to find out why a game is going slow, your Python implemented game or game server, for example, and you put a deterministic profiler on it, it's going to slow down the game, it's going to slow down the frame rate. It's not only going to make the game unplayable, but it's going to make the user behavior a lot different. So it's going to be essentially impossible to figure out what parts of something like a game are slow if you use a deterministic profiler and slow it down. And so for that, you'd like to have something that works on Windows. Okay, so now let's get into how we're going to do this. So there's this really neat function in the sys module called _current_frames. And the way you know it's really neat is because it starts in an underscore in the sys module. So something special is going on here. So sys.currentFrame basically lists each thread's current frame. And so then you can peek into the frame and figure out what's going on. So this is how pprofile works, and also oxprofile, which is the profiler I wrote. And because these are pure Python, they work on Windows, which is nice. So let's look at how this works. So again, you have the main thread. It's in, say, function 1. You call sys.currentFrames, which tells you the active frame is in function 1. You get that stack frame. You look in the stack frame for the code object. You look at the code name, and you get the function name, and then you keep track of it somehow. And then if your program goes on, another time, you wake up and you sample, and you call sys.currentFrames, and it tells you program's in function 2, and so you record the name, and you move on. Later on, you wake up maybe in function 3, repeat the same process. Okay, so I've told you some kind of high-level thoughts about why you want to do statistical profiling, how you want to do it. I'm going to give you a concrete example here with oxprofile, and then I'm going to go into kind of how it works and the logistics of the sys module. So if you wanted to use oxprofile, you would do pip install oxprofile. You would import something from the module. You would call a launch function to launch the profiler, and that's it. And then you just go on, run your code as normal, start your web server, run your game, call your URL functions, and so on. And then at some point later, when you want to see the profile, you call profiler.show, and it'll show you the profile, and you'll see what's going on in your program. And then if you want to cancel it, you call profiler.cancel. So relatively easy to use. Great, so how does it work? So this is an oversimplified illustration of the sampler loop. So we have while 1, so we're going to loop forever. And this is going to be in a separate thread, so it's not going to block your main program. We're going to do time.sleep for some interval. And then we're going to call sys.currentFrames, which gives you back a dictionary, and we're going to iterate over the IDs, which are the keys, that's the thread IDs, and the stack frames in there. Then for each stack frame, we'll look at frame.fcode.coname to get the name of the function that's executing. And then in some dictionary, we'll just increment a count. So that's it. So it's a statistical profiler and 4 lines of code, which again, Python is a really neat language, and these sys module functions are pretty impressive, that you can do something that at first might seem complicated in 4 lines of code. A couple things to mention here. So the way you control the overhead is through this interval. So you can call profiler.setInterval, and it'll change the sampling interval. So for example, if you use something like a 5-second sampling interval, it'll give you a negligible overhead. You won't even notice it. And so what we have here is a trade-off between various goals, which is accuracy, collection time, and overhead. So in a deterministic profiler, the profiler is always running and looking at each function call and keeping track of what you're doing. And that's why it slows you down, because it's doing something pretty much all the time. Whereas if you set interval to something really long, like let's say 100 seconds, almost all the time, the statistical profiler isn't doing anything. As you bring that down from, say, 100 seconds to 5 seconds, you'll get more accurate sampling of your program. As you bring it down to 1 second, you'll get even more accurate sampling. As you bring it down to, say, 100 milliseconds, you'll get super accurate sampling. And so what happens with the longer sampling times is you just have to run the program for longer so that your sampler wakes up and sees all the different parts of your program and gives you an accurate estimate. So you can tune that knob between accuracy and overhead. And in theory, if you took the sampling interval all the way down to 0, it would go to become like a line profiler, which is constantly checking what your program is doing. Another comment to mention is in some applications, you may want to add some random jitter in case you're worried about the statistical profiler waking up and somehow getting synchronized in your program and never seeing certain aspects of your program. In general, the Python threading tools tend to have enough randomness that you probably don't need this, but I mention it just in case you have some specialized application. Okay, so what does the output look like? So we call profiler.show, and we get this list. It shows the function name in the module, and the number of hits, and the percentage of the overall hits. So you notice that this statistical profile is a little bit different from the deterministic profiles that you see. That is, we don't have the time each function takes. Instead, we have a number of hits, how often we saw that. There's how often when we woke up was the program running a given function. And through that, you can get an estimate not of how long each function takes, but of how much time of your program it's taking up. So for example, in this case, send is where we wake up most often and see which function is running. And it's taking 2.8% of the program hits. So if you wanted to optimize something, in this case, you might want to optimize send. Or you might look at other functions and see like, oh, such and such, connect, let's say, is 1.5% of program hits. Maybe you expected that to be much lower. And so you can look at this statistical profile to figure out where to focus on. Okay, so now let's talk about the basic theory of sys.currentFrames. So we start a thread. This is doing mostly time.sleep. Periodically, we wake up and we call sys.currentFrames to get the stack frames that are executing and record the info from the current stack frame. And that's it. Really simple 4-line program we showed you earlier. So in theory, you can write a simple statistical profiler with just these. Now in theory, there's no difference between theory and practice, and that's just going to work fine. But in practice, there's a little bit of a difference. Okay, so let's go back to just the 2-line core of what we were showing you. So we're going to call sys.currentFrames, iterate over it, and record. Now I've started to make a few changes here, which is instead of having self.mydb just be a dictionary, maybe some other more complicated structure, and you want to call a record method just for generality and nice software engineering. And instead of just directly grabbing the co-name from the frame, maybe you want to call some function called measure tool. Maybe you want to record some other things from the frame. That's not a big deal. But the question you want to ask is, okay, what could go wrong even with something as simple as these 2 lines? So you might want to think about it for 30 seconds. Okay, so one thing that can happen is a thread context switch. That is, your sampler thread gets control. It calls sys.currentFrames to look at what's going on. It starts iterating over the current frames that are active. And then all of a sudden, the interpreter decides, okay, I want to switch to a different thread context. So it goes to a different thread, maybe your main thread or some other subthread, and comes back 5 seconds later, and you continue iterating over the frames that you've gotten returned, but now those frames maybe have gone away because the interpreter has moved on in the other threads, and so you try and read a stale frame, and depending on your Python version, you get a crash. Okay, so one thing we can do is we can use this other function called sys.getSwitchInterval and sys.setSwitchInterval. So sys.setSwitchInterval will tell the interpreter, look, please don't switch away from my thread for 10,000 seconds or whatever amount of time you give it. So here what we do is we get the current switch interval, we set it to 10,000 saying, please don't switch away. Then we do our really quick iteration over the frames, and then we say, set switch interval back to whatever it was before. So this will help reduce the problem of looking at a stale frame. There's other ways you can do it, but this is a nice way to illustrate switch interval. Okay, great. So now we're safer, more robust to context switches. Now what could go wrong? Well, anytime you're doing some kind of resource allocation, you always want to keep track of exceptions. Because if you had an exception here, it would prevent switch interval from being reset, and then your threading might start to work strangely. So this isn't really so much specific to statistical profiling, but in general, when you're doing multi-threaded code, you want to be paranoid. So here what you'd want is a try finally, so that no matter what happens, even if there's an exception, you set the switch interval back to whatever it was originally. Okay, good. So we're doing we're trying to protect from a context switch. We're using try and finally. Okay, what else could go wrong? We are just getting started in all the things that can go wrong in multi-threaded programming. So I should say, I don't want to discourage you from doing multi-threaded programming or statistical profiling. These things are reasonably robust, but you just need to be careful of all the things that could go wrong when there's multiple threads. Okay, so let's look at recording a sample. So we have this simple function record, which gets a measurement, and it's going to look in a dictionary to see, have we seen the name of that function before? And then we're going to increment, and if not, we start with a count of 0, and then we increment the count by 1. Okay, great. So we're looking in a dictionary, we're incrementing the count by 1. It's a 2-line function. Surely nothing can go wrong here, right? So what can go wrong? Well, one thing that can go wrong is imagine that you're calling this record, or the interpreter is calling this record method when it's sampling a frame. At the same time that the sampling thread is sampling a frame, somebody calls profiler.show to see the profile right now. Or some other way they decide to access the self.mydb dictionary. Then you've got one thread modifying the dictionary while another thread is reading the dictionary, iterating over it. And Python gets really upset if you have 2 threads, one of which is modifying a dictionary, another one which is iterating over it. So depending on your Python version, you'll get a crash. So what you want to do is you want to use a thread lock. In this case, I'm using threading.lock with a context manager, and then you make sure all the code that accesses MyDB uses the same thread lock so that nobody accesses the dictionary at the same time. Okay, so we've got switch the context interval. We've got use try and finally. We've got use thread locks. Seems like we're being pretty paranoid here for multi-threading. So what else could go wrong? No guesses? I don't know what else could go wrong. There's always unknown unknowns. So one other thing I would suggest anytime you're doing multi-threaded programming is use fault handler. So fault handler is this nifty little module that if you call fault handler.enable when you start your program, if you have some really bizarre crash, it'll still print out some basic debugging information. Now you're all probably used to having something go wrong and you see that nice stack trace of the exception and then you're like, oh, okay, it was function foo that caused it, let me go debug that. Now if you're doing multi-threaded code, sometimes what you'll have happen is you'll corrupt the memory. Like if you read a stale stack frame or try and modify a dictionary while you iterate over it or do some other funky stuff. And if you corrupt memory, you might corrupt the entire stack. And so when you get an exception, instead of printing out that nice stack trace, you'll get a core dump or some other really ugly crash which won't tell you what's going on. And then you'll start pulling your hair out saying like, well, where did it crash? Why did it crash? Whereas if you use fault handler.enable, when you get any type of crash, it won't allocate any new memory. It'll immediately print some really basic stuff so that even if your memory is corrupted, you'll still get something. Okay, so let me mention some additional issues. So in the sampler thread that we're using, and in general for threading, you want to set this to be a daemon thread. If you don't set it to be a daemon thread, then when your main program exits, your sampler thread would still be alive, and it would prevent your program from exiting. Whereas if you set it to self.daemon equals true for your sampler thread, then when your main thread exits, your daemon thread will also exit. Another thing to keep in mind is that, so I mentioned before that in theory, if you have the sampling interval going all the way down to 0, then your statistical profiler is going to turn into a deterministic profiler. So that's true in theory, but time.sleep currently has some minimum granularity of like 1 to 10 milliseconds. It's not really a big deal unless you're doing super high frequency trading or something where you can execute code really fast, but just worth keeping in mind. So I want to mention Flask here. So if you're using Flask and you want to use aux profile, you can use this in a very simple way to plug it in. You import a blueprint, you do app.register blueprint for aux profile, and you configure some admin users. And with just those 3 lines, you can start using this profiler in Flask. It will provide you 4 endpoints. One is unpause, which will turn on the profiler. So the statistical profiler, even though it's low overhead, it doesn't turn on by default. You have to turn it on. You can use pause to pause the profiler, so it's not affecting production. You can call status to show the current profile and the status of the results. And you can use set interval to change the sampling frequency. So again, one of the main motivations for using statistical profilers is you have some website, or you have a lot of websites or application servers or something that's deployed in production, and you want to see what's slow or what's the bottleneck or what's the program doing in real operation with real users. And so to do that, it's nice to be able to have a statistical profiler inside there, either as an endpoint or in some other manner. Okay, let's look at some additional uses. So what else can you do with sys.current frames? So again, I want to say again, like, how awesome this function is. So if there's any core maintainers in the room right now, please don't take away this function because it's just really neat. So I'm going to give you some other thoughts of ideas you could do to have fun. So what else can you do with sys.current frames? So first of all, you can do some major damage that's really hard to track down. So be careful because it lets you look into every thread that's running and mess with them. So be careful. Okay. More seriously, one thing you could do is you could take a data snapshot. That is, you could use sys.current frames to look at the active frames, and then you could periodically snapshot not just co-name, but something like frame.flocals. That is, you could take a snapshot of what are all the local variables that are active in some given function. And particularly if you're dealing with a lot of third-party libraries and you just want to know what's going on, that's kind of a nifty way, without having to rewrite those third-party libraries, to write a simple tool that can peek at what's happening in your program. You could even modify flocals. You could go into flocals and you could add 1 to every integer you find, or multiply it by 2, or do some other crazy stuff. Now, why would you do this besides wanting to cause major damage, which I'm obviously not advocating? Well, if you're running your tests, you might have invariants or assertion checks or other kind of things in your tests. Now, those tests are great for your test cases, but if you can go and randomly modify flocals, it's testing your code in a different way, which could be kind of interesting. Another thing you could do is you could do something like a statistical debugger, where you periodically snapshot some debug information, like a full stack trace and all the locals, and either dump those to a log or save those so in case there's a crash, maybe you have a random snapshot of like 10 or 20 functions that were called recently. You can do statistical code coverage, just like coverage.py, but turn it on periodically and record which lines are being executed and then turn off so you don't incur much overhead, but you can track which lines of code are being actually covered in your real use cases. So let me summarize. So profiling is designed to find bottlenecks and improve your code. You can use deterministic profiles for that, but they can be slow. So you can use a statistical profiler to sample your code periodically. It'll let you use your statistical profiler in production to see what real users are doing without providing too much overhead. You can use OxProfile, which is open source and on GitHub, or you can write your own in really not that many lines, provided you're careful of a few things. The key functions here are setProfile, setTrace, and sys.currentFrames, which lets you peek into what the interpreter is doing or have the interpreter call your function periodically. And it's simple in theory, but anytime you're using threads, be careful, use try finally, use locks, maybe use a switch interval, and use fault handler. So that concludes the main talk, and ready for Q&A.
We've got a few minutes for questions now. Please, if you have a question, just use one of the microphones here.
Hello? Hello? Can you hear me? There we go. My question is, with regard to statistical profiling, in the example you gave where the number of hits kind of tells you what to go look at for potential improvement, how do you differentiate the fact that that number of hits may be due to just the fact that that particular program, let's say a web crawler, right, would obviously have a huge percentage of hits on like request.get or whatever, versus that number of hits suggesting that those particular function calls are slow or need improvement. Does that make sense?
Yeah, so let me rephrase what I think you're asking. So I think what you're saying is, what if you have something like request.get, which is not really slow in CPU terms, but it's slow in the sense of time, that you just have to wait for things to go back and forth on the network. So it's not CPU bound, but it's still slow. And the statistical profiler would be telling you, like, it's slow. Most of the time in your program, you're waiting in this particular function. So one thing you could do is, if you know that's the case, you can just ignore that line and go down and look at the other things. There's not a ton of stuff you can do because the fact that the Python interpreter is sitting there waiting in there is going to be hard to figure out in a profiler because it really is a slow function. Does that answer your question? Or does that get at what you're saying?
Sort of, yeah. It was more how do you, like, request.get was just an obvious example, but really what I'm getting at is how based on what you're seeing from a statistical profiler, what clues do you have that can help you differentiate that a function call actually needs improvement versus that is just used a lot in the program?
So, okay, so that's a good question. It's not so much a statistical versus deterministic profiling question. It's just a question of how do you know if something is slow or it's just called a lot. So a profiler can't help you so much with that. That's more something you have to figure out. And so the way to think about a profile is not necessarily so you can look at what's the top hit or what's the slowest function. And the more you can speed that up, the better your program will be. Or you can look for what functions seem to be taking a lot more time than I expect. And you can use that to drive what you look at.
Okay, thank you.
Maybe on this side?
Yeah. Have you any experience with running a statistical profiler inside a Docker pod?
Inside a what?
Docker.
Docker.
Kubernetes.
So it should work just fine so statistical profiler should work just fine in Docker or Kubernetes because it's running inside the Python interpreter. And it's just telling you, when the interpreter is running, what function is it in most often? Does that answer your question, or did you mean something different that I misunderstood?
I was wondering if the fact that you're really faking that you're on a process, you're on one processor, but you're really sharing a processor, does that change your statistics?
It won't change your statistics. It might, if for some reason your particular Docker process gets shoved to the side while other things run, then that could be an issue, of course. But that's not really a problem you can solve with profilers. Back to this side.
Just kind of on the same note, first of all, great talk. This is really educational. Also, in terms of like, messing with things like such as like context switching, how far down is that propagated down? Is that just propagated down to the Python interpreter? If it's like running on like a virtual machine or with this like hypervisors and stuff involved, like it's not safeguarded against that, right?
Good question. So the context switch, the set switch interval is only going to protect you from a context switch happening in the Python interpreter. It won't protect you from the operating system deciding which process gets to run. So that's true. But the thing that we were worried about in that example is that if the Python interpreter switches away and then switches back to you, you've now got stale stack frames potentially. And so you're looking at stale memory, and so that'll cause potentially a crash. There's other ways you can try and check if those stack frames are live or stale, but that's one simple example. Back to this side.
Hi, thank you for the talk. 2 questions. First, have you had a chance to measure the performance implications, say with a 100 millisecond sampling? And second question, have you considered recording, let's say if a function A calls function B and you ended up seeing that the function B was called, that also implies that function A was called, so the counter for the function A should also be incremented, and that might address one of the first questions there was.
Excellent question. I'm glad you asked that. So let me answer this. So let me take that in order. So if you set the sampling interval down to 100 milliseconds, the sampler is going to run more often. It's hard to say anything concrete because if you're running on a 15-year-old laptop, running it every 100 milliseconds is going to mean a lot more than if you're running it on like a top-end Xeon server or something. Now, the actual time for the sampler to run is relatively small, but that's what matters. How long does it take the sampler to run relative to the sampling interval? And that's how much overhead you're going to have. Okay, so the second question was, what if function A calls function B calls function C? So let me go back to a diagram we had earlier, right here. So we have foo call bar, call baz, call boo. So because you have f back, what you can do is you can say, okay, I'm in frame number 4, which is boo, but that was called by baz, which is called by bar, which is called by foo. So one thing you can do in your statistical profiler is say, don't just count the function I'm in, also add a hit to each of the callers. So I didn't show that just to keep things simple, but in Ox profile, you count not just the function you're in, but all the callers. So you'll capture that if there's some top-level function calling everybody.
Thank you.
Do we have time for more, or are we done?
One more?
Okay, that's all the questions, I think. Sorry, I'll be outside in the hall if there's more questions.
Thanks, Emin.
Thank you.